Okay, so we're going to take a look at the word problem examples for chemical equations. So the very first one, number one, started off with aqueous lead nitrate. So we're going to go ahead and put our little line there for our coefficient. Lead, we look it up on the periodic table. Here's lead. And the nitrate, this is one of your polyatomic ions that you should have memorized. And we're going to put this little AQ because it's aqueous. All right. And then we're going to have, it says reacts with, so we're going to put a plus. Reacts with potassium iodide. So potassium iodide. And it says it's also aqueous, so AQ. To form, that's our yield symbol. That's really super important. Lead iodide. And so lead iodide. And it doesn't say what it is. It doesn't say if it's aqueous or not. So we need to think of this as it is most likely a solid. And aqueous potassium nitrate. Okay, and that says it's aqueous, so we're going to have our little AQ. All right, so that's our skeleton of our balanced equation. Now, with this, we need to go back. We need to look at the ionic charges just to double check that our formulas are correct. Notice I said this is a skeleton. This is just taking the words and from the problem and just writing them down. So let's go back. It said that it's lead 2. So we know that this is going to be a +2 charge. And so over on this side, it's a +2. Okay, nitrate is a -1. So we have a -1. Potassium is a +1. Now I'm getting these ionic charges, remember, from, and iodine's a -1. So I'm getting these ionic charges from the top of your periodic table where it says ionic charge, except for nitrate, because nitrate is a polyatomic ion. And then what I'm going to do, especially for the ones, if it's 1-to-1, I don't have to worry about doing a crisscross. But these, I have to worry about doing a crisscross. See that? So I'm going to crisscross these formulas, these ions, so that I now get the correct formula. So lead is going to have a 1. I'm not going to worry about that, but the nitrate's going to have a 2. So because of that, I need to put this in parentheses and put the little 2 out there. Okay, same thing over here. I'm not going to worry about the lead. The nitrate, I need to put a 2. Okay, and of course, if I crisscross 1 and 1, no big deal. The formula stays the same. Formula stays the same there. Okay, now I can start listing and doing my atomic inventory. So we're going to start right here with lead. Right underneath the yield symbol, I'm going to put my lead. I'm going to put nitrate as a group because nitrate is also over on this side with the products and reactants. So I'm going to keep it as a group instead of breaking up the N and the O. So NO3 stays together. I'm going to put my potassium and my iodide. Okay, so on my reactant side, I'm going to go ahead and list. I have 1 lead. I have 2 of the nitrates. I have 1 potassium and 1 iodide. Over on this side, I have 1 lead again. Okay, so I'm on the product side. I have 2 iodides. I have 1 and 1. So 1 nitrate, and 1 potassium. Okay, so if I take a look here at my balanced equation, I see my iodide is definitely off, my nitrate is off. So, we need to sort of attack those where there's 2s, all right? So if I have a 2 here for nitrate, let's go ahead and get 2 nitrates for this side. So if I plug a coefficient 2 in here in the problem, we now have the 2 distributes to the entire nitrate. So this is going to cross out and become a 2. But the 2 also distributes to the potassium. So now my potassium changes to 2. Okay, so I've now balanced or done my inventory again. Now I need to take a look at this side. We see here the only thing that's balanced is my lead and my nitrate. I now have my potassium and my iodide are off. So I'm going to take a look here. I'm going to plug a 2 in as a coefficient in my potassium iodide. By doing that, my 2 now distributes to the potassium. I now have 2 potassiums. My 2 then distributes to the iodine, and I now have 2 iodine. So I've now done an inventory again. So notice I have to keep going back and forth. Now, if I do that, I notice my iodine's balanced, my potassium's balanced, my nitrate's balanced, and my lead is balanced. So now I have a balanced equation. I take a look back up here, and I need to plug a 1 in for lead, nitrate, and I need to plug a 1 in for lead iodide. So now I have a complete balanced equation. I have a ratio of 1 lead nitrate to 2 potassium iodides, which yield 1 lead iodide to 2 potassium nitrate. So this is what it would look like if it was a ratio. 1 to 2 yields 1 to 2. Okay, so that's what it looks like. Again, these coefficients are really super important even later on with stuff that we're going to get into. Okay. All right. So let's take a look at the second problem, which is, I think, more simplistic in many ways. Okay, so problem number 2. All right. So with this one, it says we start off with potassium. And there is nothing else there, so we know it's going to be a little solid. Okay, reacts with water. And of course, you guys all know water is aqueous. We don't even need to put that down. To form, there's our yield symbol, potassium oxide. And hydrogen. Okay, again, this is just taking the words right out of the word problem and making a skeleton for a balanced equation. Now let's go back and double check. Potassium, that's a good formula for potassium because it's all by itself. Water, we know the formula for water, H2O, good formula. Okay, potassium oxide. Let's double check by going up to the top of our periodic table and looking at the ionic charge. Now the ionic charge for potassium is a +1. But for oxygen, it's a -2. Okay, so that lets us know right there we need to do a crisscross. And by crisscrossing this, obviously potassium needs a 2. And our oxygen just gets a 1. Okay, and then we need to go over here to hydrogen. The hydrogen, well, hydrogen, see, it's not a polyatomic ion, but it is that other thing I asked you to memorize, which would be a diatomic molecule, di meaning 2. Okay, so now we have our actual formulas. Now we need to go ahead underneath our yield symbol. We need to list our elements. So we're going to start right here. We have potassium, we have hydrogen, and we have oxygen. Potassium, we know on the reactant side, we have 1, we have 2 hydrogens, and 1 oxygen. Okay, on the product side, we have 2 potassium right there. We have 2 hydrogen, and we have 1 oxygen. Okay, so we see right now that our oxygens and our hydrogens are balanced, but our potassium is definitely way off. So this is a single. We want to do the singles always last, okay? just because we need to do them last. So what are we going to attack here? Well, we need to take a look at, let's see, we don't have to worry about hydrogen, and we don't have to worry about oxygen by any means. So what we do need to take a look at, well, then is the potassium. So let's go ahead and plug a 2 in here for a coefficient. 2 distributed by potassium is going to give us 2. So look how simple this equation was. Our potassium's balanced, our hydrogen's balanced, and now our oxygen is balanced. We're done. So now we have to just go back in and plug in these blank spots for the coefficients. Plug in 1 for the coefficient, and we are done. So ratio-wise, we have a 2 to 1, 2 potassiums to 1 water yields 1 potassium iodide to 1 hydrogen molecule. And so again, that was a lot more simplistic. Okay, we only had to do crisscross once, but we did have a diatomic molecule. And we didn't have to worry too much about whether it was aqueous or gas or anything of that nature. Okay, now for the challenging problem. And hopefully this gave you guys some challenges, and hopefully you were working with it. Okay, so let's take a look at problem number 3. Now, problem number 3, like I said, was definitely much more challenging. And luckily it gave you, right from the get-go, it told you about the ethane gas. So we already know the formula for ethane gas. It's C2H6 with, so there's our plus sign, with oxygen to form, so there's our yield, carbon dioxide, carbon dioxide, so 2 oxygens, and water. And of course, that's a formula that you know. Okay, so again, this is a skeleton of the balanced equation. And the reason I say it's a skeleton, because we've just taken the words, that's it, and put them down as formulas. Now, we need to double check if the formulas are correct. Ethane, we don't have to worry about. Oxygen. Let's see, is that the formula for oxygen? Well, is it a polyatomic ion? No. Is it a diatomic molecule? Oh, yes. So we need to plug a 2 in here so we now have the correct formula. Okay, carbon dioxide, we know that's the correct formula, and you already know the correct formula for water. Okay, so now we have a balanced equation. We don't have to worry about doing any crisscrossing. We have all the correct formulas. So let's now do an atomic inventory. Carbon, hydrogen, oxygen. Okay, on the reactant side, we have 2 carbons, 6 hydrogen, and 2 oxygens. On the product side, we have 1 carbon, we have 2 hydrogens, and how many oxygens do we have? Well, we start off with 1, 2, plus another 1. So 2 plus 1 is 3. Okay, so that's a really odd number to work with, is that 3. And so it really becomes a real pain. So we want to go after oxygen, okay? And we want to go after oxygen on this side of the problem. So normally we would plug like a 2 in here. 2 times 3 would be 6, but that doesn't make sense, because if we plug a 2 in here, that'll give us 4. That's not too bad. But we end up having some really odd stuff that goes on. So let's not worry about that one just now. Okay, so let's go after the carbon. Carbon is off, hydrogen's way off. We'll look at hydrogen here in a bit. Let's take a look at the carbon. Okay, I need to have 1 more carbon here. So if I put in 1 more carbon here, let's see, if I put a 2 there, that gives me 2 carbon. Okay, and so this is where you now end up playing around. Now you sort of have to guess. Always do this one last, okay, because it's all by itself. So you want to look at the other 3. Now, whatever number you plug in here, or sorry, you plug in here, you have to remember that this oxygen, so if we plug in a 3, that's 3 oxygens. That creates a problem because 3 plus the 2 or whatever other number this is going to be even is going to always give us an odd number. And we need to come up with an even number because we have an even number over here. So let's see. Well, we could, and we're just going to play around. Let's plug in. We know we have 6, so let's go ahead and put 3 there. Again, that's going to be a problem because 3 times this 1, that gives us 3, 4, 5. Well, that's not going to work. So we now need to go with another number. Let's maybe double that. So let's plug in a 6 here. If I plug in 6, okay, that 6 is going to distribute to the hydrogen. That gives us 12 now. Man, that's a big number, but that might happen. 6 times 1, that's 6, 7, 8 oxygen. Okay, so we're going to have 8 oxygen. So that's what we have now. Let's look at the other side. Okay, again, we're going to deal with oxygen last. So let's go ahead and go after this hydrogen. We have 12 on this side, so we need 12 over here. If I plug a 2 in, now that 2 is going to distribute by the carbon of 2, so this becomes a 4. 2 is going to distribute by 6 for the hydrogen. That gives us 12. Okay, so our hydrogens are balanced. All right, so let's go ahead and look over here at this one. Okay, so now if we look here, well, we have 4 carbon and 1 carbon. So let's plug a 4 in. By plugging a 4 in, 4 times 1, being this 4 distributed, times 1, that'll give us 4. Okay, so now our carbons are balanced, our hydrogens are balanced, but this 4 is also distributed by the oxygen. And so 4 times 2, that gives us 8. So 8 plus 6. 8 plus 6, man, that's 14. That's another big number. Okay, so I've done inventory again. My carbons are balanced. My hydrogens are balanced. My oxygen is way off. I only have 2 on the reactant side and 14 over on the product side. Well, this isn't too bad. 2 goes into 14 how many times? 7 times. So we're going to put a 7 in here, and 7 times 2 being 7 being distributed. 7 times 2 is 14, and we end up having 14 oxygen. So now our inventory down below is balanced. We plugged in a number in each of these spots up above in our coefficients, and we see that we have a complete balanced equation. Now with this, we need to take a look at the ratio. So we have a 2 to 7, so 2 ethane gas molecules to 7 oxygen molecules yields 4 carbon dioxide and 6 water molecules. Okay, so that's perfect. That's our ratios. Now, one last thing to double check. We want to see if this can be reduced down at all. So like if we could divide every single number by 2, then we know that we've maybe inflated this, okay? But that's not the case. 2 cannot go into 7. So this is a completely balanced equation, and that is how you would end up doing this. Again, when we're working down here, sometimes it's sort of guessing. You're plugging in numbers. All right, you saw I initially plugged in a 3. It didn't work, so I erase it and I plug something else in. So don't get frustrated. Some of the problems when they're bigger like this just takes a little bit more time to work with. Okay? Remember, you're looking to get it to balance out.